Today, we're diving into the state of matter we're swimming in every single second, but can't actually see: gases. You'd think they're pretty simple, right? Mostly just empty space. But the thing is, gases are run by a set of invisible laws. Laws that are so predictable, they can explain everything from how a car tire stays inflated to why a hot air balloon flies.
Just think about it for a second. What if you could actually see the air? You wouldn't see emptiness. You'd see trillions upon trillions of tiny particles in a constant, frantic dance, literally bouncing off each other and everything around them at hundreds of miles per hour. It's this hidden, chaotic ballet that defines the world of gases.
So, here's our game plan. First, we'll explore the basics of this invisible world. Then we'll get into the Kinetic Rulebook that explains why they act the way they do. After that, we'll look at the simple gas laws, build our way up to the master equation, PV equals nRT, and finally, see what happens when theory meets reality.
Okay, so first things first, what really makes a gas a gas? What's the deal? It all boils down to a handful of unique characteristics that make them totally different from liquids and solids.
And you know, all of these properties are really telling us the same story. Gas particles are super far apart and they just don't care about each other. They fill any container you put them in because they aren't stuck together. They're easy to squeeze because there's so much empty space between them. And that constant, random motion, that's exactly why smells can travel across a room.
So people could see what gases did for centuries, but the big question was always why. That's where the kinetic molecular theory comes in. You can think of it as the fundamental rulebook for how gases are supposed to work.
The idea at its heart is actually incredibly simple. A gas is just a giant swarm of tiny particles, all zipping around randomly. And what about pressure? You know, the feeling of air in a tire? That's nothing more than trillions of those particles constantly smacking into the walls of the container. It's a beautifully simple model that explains so much.
Now, to make the math for this model work perfectly, scientists came up with the idea of an ideal gas. And an ideal gas follows these 5 rules. Its particles are tiny, they're always moving, and when they collide, it's a perfect bounce. No energy is ever lost. But crucially, the model assumes 2 big things. The particles themselves take up 0 space, and they have absolutely no attraction to each other. Now, keep those last 2 in mind, because they're going to be really important later on.
So, way before the whole kinetic molecular theory was figured out, scientists were in their labs just messing with stuff. And they started noticing these super predictable patterns. These became the simple gas laws, and they were the first breadcrumbs leading to the bigger picture.
First up is Robert Boyle, all the way back in 1662. He figured out something absolutely fundamental. If you keep the temperature of a gas the same, its pressure and volume are inversely related. They're like 2 ends of a seesaw. When one goes up, the other has to go down.
And it just makes sense, right? You crank up the pressure. You're literally squeezing those gas particles into a smaller box. That's a lower volume. Then you release that pressure, and they immediately expand to fill whatever space they can. More pressure, less volume. It's as simple as that.
And this neat little relationship gives us an awesome predictive tool. P1V1 equals P2V2. It's the mathematical proof of that seesaw action.
Fast forward over 100 years, and Jacques Charles adds the next piece to the puzzle. This time, he's looking at temperature. And what he finds is that if you keep the pressure steady, a gas's volume and its absolute temperature move in lockstep. One goes up, the other goes up.
And this ties perfectly back to our kinetic theory. Heat is just energy. So when you heat a gas, its particles start zipping around like crazy, pushing outwards on the container, and boom, the volume expands. Cool it down, they get all sluggish, and the volume shrinks. And the math is just as clean. The ratio of volume to temperature is always constant. This gives us another really powerful but simple predictive equation.
The final piece of the simple law puzzle is Avogadro's law. This one connects volume to the actual amount of gas you have. And it might be the most intuitive one of all. If you have more gas particles, well, they're going to take up more space. More gas, more volume. Makes perfect sense.
All right, so we've got these 3 separate relationships: volume and pressure, volume and temperature, and volume and the amount of gas. So what happens when you put them all together? Well, you get one of the most powerful and famous equations in all of chemistry. So let's build it up. From Boyle, we know volume is proportional to 1 over the pressure. From Charles, we know it's proportional to temperature. And from Avogadro, it's proportional to N, the amount of gas.
You combine all of that, and you find that volume is proportional to N times T, all divided by P.
And with just a little bit of algebra, we rearrange it and we arrive here. PV equals nRT, the ideal gas law. This is the big one. This single equation links pressure, volume, the amount of gas, and temperature all together. If you know any three of those things, you can calculate the fourth for any ideal gas anywhere in the universe. It's just incredibly powerful. Now you're probably looking at that R and wondering, what's that? R is the ideal gas constant. You can think of it like a universal conversion factor, a magic number that makes sure all the units, liters, atmospheres, moles, Kelvin, all play nicely together. Its value changes depending on the units you're using, but its job is always the same, to make the whole equation work perfectly.
Okay, so it's reality check time. The ideal gas law is amazing, but remember, it's based on those ideal gas assumptions. And real gases, out here in the real world, well, they don't always play by those perfect rules. So where does the model start to break down? It's those two assumptions we talked about earlier. The ideal model pretends gas particles have zero volume and zero attraction for each other. But in reality, of course, molecules have a tiny bit of volume, and they do have weak little attractive forces that can pull them together.
But here's the key. The ideal gas law is still incredibly useful because under most normal conditions, real gases behave almost ideally. This is especially true at low pressures, when the molecules are so far apart that their individual size and their little attractions just don't matter. And it's also true at high temperatures, when the particles are moving so fast that they just blow right past each other without time for any attractive forces to take hold.
For those times when the deviations really do matter, like at super high pressures or really low temperatures, scientists needed an upgrade. The most famous one is the van der Waals equation. You can see it looks a lot like the ideal gas law, but it's been modified. It tweaks the pressure and volume with these constants, A and B, to correct for those real-world attractive forces and the actual volume of the molecules.
So, we've seen how this chaotic, invisible dance of gas particles is actually governed by a set of clear, predictable laws. We can squeeze them, we can heat them up, and we can predict what they're going to do with amazing accuracy. Which kind of leaves us with one last big thought. If we can manipulate a gas so much, what happens when we push those conditions to the absolute extreme? What does it take to force those free-roaming particles so close together that they stop being a gas at all?